Hello everybody, welcome to today's lessons. Today we are looking at trees and minimum spanning trees. So basically this is still involving our networks and looking at the graphs. So a subgraph is what we're going to start with. A subgraph is basically a graph that exists within another graph. Okay, so it basically contains all of the vertices and all of the edges from the original graph, but it might be drawn a little bit differently. Okay, so if we look at this one here, this graph shows the exact same information that is shown on our graph over here. Okay, so it would be known as a subgraph. So if we look here, there's a connection between J and N. Okay, there is a connection between J and N. There is a connection between N and K. Oop, yep, there is. There's a connection between K and M. Oop, yep, that exists. There's a connection between N and M. Yep, that exists. So this is a subgraph of that one there. So what we have to do for questions, just to determine whether each of the graphs below is a subgraph of this graph drawn on the right. Okay, so let's start off with A. All right, so if we look at all the points, D to E, yep, D to E exists. D to G, yep, that exists. D to I, yep, D to I exists. D to F exists. F to H exists, and then G to H exists. So yes, A is a subgraph. If we look at part B, okay, the point A, B, and C, A to B, if we look here, A to B exists, B to C exists, and A to C exists. So yes, this is a subgraph. Even though the orientation of the B is slightly different, it shows the same information. If we look at C, we've got the point A to B over here, which yes, that exists. B to C, yep, that exists. C to D, ooh, C to D does not exist on the original graph, so no, that is not a subgraph. Okay, so this is basically how you would go about working that out. Beautiful. Go to the part D. So we go A to B, yes, it exists. A to C, yes, it exists. B to C, yes, it exists. C to E, yep. A to E, yep. E to D, yes. G to H, yes. H to F, yes. F to I exists, yep, even though the orientation is slightly different. And C to F exists. So yes, this one is a subgraph. Okay, and then the final one, if we have a look, A to B, yes. B to C, yes. C to F, yes. F to D, yes. F to H, yes. F to I, yes. I to G, yes. A to E, yes. E to G, oh, there's no line from E to G, so no, that is not a subgraph. Okay, so this is just a yes or no question. So the next bit that we look at is what we call our trees, or our minimum spanning trees. Okay, so a tree is basically a connected graph or a subgraph that doesn't contain any loops, any multiple edges, or any cycles. Okay, so it's a component. So this one here would be considered a tree. Okay, this one here would not be considered a tree because it has a cycle. So we can go from A to B to D to C to A. So that contains a cycle, so it's not a tree. This one is also not a tree because it is not a connected graph. There's no way to go from A to B. Okay, so that would not be a tree either. So a tree has to be connected and it can't contain any loops. So remember, a loop is if for E I were to draw like a point like that, an edge like that, that would be considered a loop. So that wouldn't be a tree. Any multiple edges, so from B to E, and then we had like another one going that way, or a cycle like we can see. A spanning tree is basically a tree of a subgraph that includes all of the vertices of the original path. So all of the vertices of the original graph need to be included. So what we can do is we can see every connected graph contains one or more trees, and a tree with n vertices is going to have n minus 1 edges. So if it has 5 vertices, it's going to have 4 edges because 5 take away 1 is 4. If it has 3 vertices, okay, it's going to have n minus 1, so 3 minus 1 edges, which would be 2 edges, is what that rule is referring to. All right, worked example number 12. Determine whether each graph below is a spanning tree of the graph shown and verify that each spanning tree has n minus 1 edges, where n is the number of vertices. All right, so if we look at part A, we can see that this is a connected graph. All of the points are connected, so it meets that requirement. It has all of the vertices of the original graph, C, B, A, E, G, I, H, F, and D all exist on the original, and it contains no loops, doesn't have any multiple edges, and it doesn't have any cycles in it. So A would be considered a spanning tree, okay? And the second part says, verify each spanning tree has n minus 1 edges. So if n is the number of vertices, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, which means it'll be n minus 1, so 9 minus 1, which is 8 edges. So if we count 1, 2, 3, 4, 5, 6, 7, 8, which works out. All right, let's look at B. So if we're looking at B, straight away I can see here that there is a cycle. So straight away I know that that is not a spanning tree. If we look at part C, this H is not connected. So straight away there's an isolated vertex, which means this is not a spanning tree. If we look at part D, there is no connection between what I've just circled and this one over here. So straight away they're not connected. It's not a spanning tree. And last one, the graph is connected. All the points, we can follow some sort of path. There's no loops, there's no multiple edges, and there's no cycles. So yes, that one is a spanning tree. And if we look at that one there, the number of vertices, so n is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, which again means 9 minus 1. N minus 1 equals 8, which is going to be 8 edges, which if we count 1, 2, 3, 4, 5, 6, 7, and 8, which is correct. All right, moving on to now minimum spanning tree. So we've identified what a spanning tree is, now calculating minimum spanning trees. So a minimum spanning tree is basically a spanning tree for weighted graphs. So they have numbers associated with each of the edges. Okay, so this could be the time that it takes to go somewhere, the distance on that path, and it basically could represent the cost, the time, or the distance, we just said that, between all of the vertices. So the minimum spanning tree basically has practical applications. So it's going to be for like your worded problems, such as finding the minimum length of pipes that might be required in a water system, or the minimum length of pathways that might connect different buildings, things like that. So usually we're trying to find the minimum pathway that we can follow. And to do that, we use something called Prim's algorithm. Prim's algorithm is basically like a rule that we can follow to try to figure out the minimum spanning tree. Okay, so it's like a bunch of steps, which is shown on the right over here. So what I have as an example of this is the map on the right outlines where certain buildings are within a university. So the vertices represent the buildings and the edges represent the paths, and the numbers on each edge represent the distance in meters. So we might be asked a question that goes along the lines of the maintenance team at the university. They want to cover some of the paths that no matter which building the students need to go to, they're able to stay dry when it's raining. So they might need to go a certain way so that they can remain under cover. So the team want to achieve this by covering the shortest distance possible. They want to save materials. So we can use Prim's algorithm to find the minimum spanning tree to solve this. Okay, so basically what we would do is, looking at our original network, which is up here, we would choose any vertex that we want to start at. So let's start, say, at this one here, W2. What we're going to do first is we're going to find the edge with the lowest value that connects the vertex that we've just chosen to another vertex. So if we look at this, the two edges coming off are 180 and 390. So the shortest one is 180. So I'm going to highlight that one. We then look at all of the edges connecting those two vertices and choose the edge that has the lowest value again. So here, this one connecting to the next one is either 350 or 400. 350 is the lower number, so I'm going to follow that one. And then we look here. So we need to get down to S2 and S3 as well. So if I follow this pathway, obviously I'm going to have to go down 190. But if I choose going this way, I've got to go down 180 and down 1 to 200. But I could go that way by going 180 and then 190, which would actually be a closer distance. So we can then get rid of this line here because that's going to add up to being more. All right, so we've connected this side, and now let's look at this side. So looking at C, if we need to get to the ends up here, we're going to have to highlight that 200, okay, to get from N1 to N2. I can go via 180, and then is it quicker to go N3 joining to 220 or 190? Well, it's closer to join 190, okay, so we're going to join that one. Now we need to get to E1, so am I going to follow 270 or 350? We're going to follow the shorter path, which is 270, and then down here, of course, the closest one to get to E2 is going to be 180. So what we've done is we've created our minimum spanning tree for our network. So you basically keep repeating what we've done until all of the vertices in the graph are included, okay? So if there's more than one edge with an equal lowest value, then you can basically choose either one, okay? But we're aiming to follow the shortest path. So if we look over here, we've got some examples. Down here, I'm just going to create some extra space so we can do some drawing. And if I zoom in, that'll allow us to draw over this image. All right, and we're going to draw in green this time. So we've got Edgar here. He wishes to connect electricity to 8 sites in a caravan park. The weighted graph shows the distances between each site and the location of the electricity source, P. Okay, so we can see that if P is our electricity source, all of them are coming off of that. We want to use that Prim's algorithm, so those steps that we just went through, to find the smallest amount of electric cable that might be needed to connect all 8 of these sites. So basically, we're going to choose P as our starting point, okay, and we're going to select the edges with the shortest length. So if we look at all of them here, our shortest length, we've got 16, 17, 11, 16, 14, 13, 10, 13. Okay, the shortest length is this 10. So I'm going to join these two first. And then coming off of that, off of this vertex that we just drew, we're going to see which one's shorter. So is 7 shorter or 8 shorter? Or 7's shorter. So let's highlight that one. Okay, so we've got S1 included. And then going this way, we have to also look at what things are going to be like going down. Okay, so we're going to show the shortest one connecting down here, which would be for S3, the 8 number, the 8th edge. And then we go down here, is 13 shorter or is 9? So we're going to go with the 9. Okay, and then we're going to get to this point. Let's look on this side now. So we're going to choose the shortest path from P. The next one that was the smallest was 11. So let's go with the 11. It's a little bit of trial and error as well. Yeah, but once we've chosen the 11, we can basically start to connect upwards. So is it easier, how do I get to S5? Is it easier to go via 19, 16, or 9? Well, 9 is the shortest, so I'm going to connect it that way. And then here, is it easier for me to get to P to S8 via 16 or 18, or can I go another way? Maybe we can connect this S7. So if I go via this, is it easier to go via 17 or 10? It's easier to go via 10. Here, the next shortest one, am I going to choose 16, 8, or 18? The shortest is 8. And we have now connected all of our vertices, okay, with the smallest amount of distance. So what we would do is actually now answer the question, what's the smallest amount of electric cable that would be needed? I add up all my numbers. So 7 plus 8 plus 9 plus our 10 that was here plus the 11 plus the 8 plus the 10 plus the 9, and they are